All right, morning everyone. Just a piece of practical information to begin with. We'll have a reference group meeting at the end of the second lecture today. So basically that's your opportunity to give some feedback on this course, how you feel about the lectures, the exercises, the curriculum, the compendium, etc. So the last 10 minutes or so of the second lecture today, you can have your say. And then I will meet with the reference group after that and discuss your feedback. So just to briefly recap the main content of the previous lecture, we had a look in particular at various orbits that a particle could take when moving in a central force field. And we discussed how these orbits would depend on the energy of the particle. So for instance, you could have unbound motion if the energy of the particle was sufficiently high. But you would also have this centrifugal barrier as the particle would approach the orgo of the force center. Alternatively, you could also have bound motion if the energy of the particle was sufficiently low, in such a way that the radius that the particle could be positioned in would have to be confined. And we discussed this mainly qualitatively. So what we'll do today is basically to have a quantitative look at this. We'll actually take a specific potential, which is central, known as the Kepler problem or the Kepler potential, and actually solve analytically for the orbits that are obtained from this potential. So that's on the menu today. The Kepler problem. So we're considering a force which is central, and which can be written like this, where K is a constant. The associated potential with this force can be written like this. This is just minus the gradient of the potential. So the task at hand, what we want to do here, is to find an analytical expression for the trajectory that a particle will take when moving in this potential. So that's the main task at hand. Now, to do so, we need an equation of motion, something which relates the evolution of the coordinates used to describe the particle to time. And a suitable equation of motion for our problem is this one. There are two important comments regarding this equation, how to obtain it. So for one thing, we see that it's purely dependent on the radius. There's only a radial dependence. There's no dependence on angle. The reason for this is that we managed to eliminate the angular dependence by using the conservation of angular momentum, which we substituted in here. So we use that theta is a cyclic coordinate if the Lagrangian only contains central potentials. And so we could eliminate theta dot and insert the angular momentum instead. And in addition, this equation of motion arises from the conservation of energy. So what we've done here is just to rewrite the conservation of energy in a way that isolates r dot. There are two ingredients here, conservation of energy and conservation of angular momentum. We can rewrite this in a form which is more suitable for integration. Like this. Now, the particle moving in this potential is in general characterized by two generalized coordinates, r and theta. So by integrating this equation, we can obtain the radial dependence on time. But if we're interested in the angular dependence on time, we can substitute d theta into this equation. So to find an equation of motion which gives us the angular dependence with time, we can substitute this conservation of angular momentum. This is the canonical momentum for theta, which can be written like this. So substituting that into this equation, we get the following. So one viable, it's not the only strategy possible, but one viable strategy to solve this problem would be to first integrate this equation, obtain r as a function of t, and then solve this equation, integrating on both sides and then substituting r as a function of t into this. Now, the formal solution of this equation reads where this is some integrational constant. Okay, so far this is completely general. We haven't specified the potential energy in any way. So let's now substitute the Kepler potential into V. So we let V equal minus K over R, and then perform a change in variables to be able to solve this integral. Because if we introduce this variable, we're able to get rid of this pesky r squared here, since the differentials of u and r are related by this factor. And so we obtain this equation here, which looks, I think, a little bit better than this one in terms of finding a solution. Now, we've introduced two integrational constants here. We're integrating from R0 to R, and so hence from theta 0 to theta. But we haven't said anything about what these initial conditions actually represent, what they are. They're just two constants so far. So let me make a choice now, which I will substantiate for you later on. So I choose theta 0 equals 0. What I will show is that if we choose theta 0 equals 0, then that corresponds to a situation where the polar angle theta is being measured from the perihel. And the perihel is in general defined as the points on the trajectory where the particle is closest to the orgo, or the center. Now, keep in mind that I can make this choice actually without any loss of generality. It just corresponds to some choice for initial conditions. It just corresponds to some choice of relative what point this polar angle is measured. And whereas it isn't obvious now, we will see when we obtain the final solution that theta 0 equals 0, which is convenient because we get rid of this, it actually corresponds to the period. So we'll see this. Now, if you use Rothman or any other mathematical formula collection, you will see that this integral is a standard integral with a known solution. So this is just something you can look up. I should also define here the quantity q, which I define as follows, in terms of these parameters, alpha, beta, and gamma. So if we compare now this standard integral with our formula for theta, we see that we have to identify the following parameters. Which will give us the same form. So with our choice of theta 0 equals 0, we now obtain the following solution for theta. Which looks a bit disheartening perhaps. We have theta equals minus arc's cosine of some complicated function here of r. But we can actually simplify this expression. So the first thing we can do is introduce this parameter here, epsilon, which I just defined like this. And this is known as the eccentricity of the orbit. Let me also make a convenient choice and define this orbit parameter p, which essentially is a measure of how much angular momentum you have compared to the strength k of the potential. If we now introduce these two quantities, the eccentricity and the orbit parameter, we can write theta like this. If we now make use of the fact that cosine of some quantity is equal to cosine of minus that quantity, we get this by taking cosine on both sides. And this is a pretty neat form, I think, for r as a function of theta. So it describes how the radius of the trajectory of the particle depends on the angle. And it's expressed solely in terms of these two parameters now, the orbit parameter p and the eccentricity epsilon. So one special case that we can perhaps infer immediately is that we see that if r, the radius, is independent on the angle, we should have a circle, meaning r is constant, which is the case if epsilon is 0. So if the eccentricity of the orbit is 0, we have a circular orbit. We'll say a few more words about what kind of orbits we have in just a moment, but let me now revert to my statement here that if we choose the integrational constant being equal to 0, it corresponds to the polar angle being measured from the perihelia. So let's now see if that's the case. Now, cosine of theta varies between 1 and minus 1. So you see that when this term here, 1 plus epsilon cosine, is at its maximum value, r is at its minimum value. So cosine, 1 plus epsilon cosine will be maximum when theta is equal to 0, which means r will be minimum when theta is equal to 0, which is precisely the definition of the perihelia. On the other hand, when theta is equal to pi, we have the maximum radius attainable. So by using this rather compact expression actually for the trajectory of the particle, we can now classify various types of orbits depending on these parameters, p and epsilon. Now, I would suggest to you that it's this parameter, the eccentricity, which is the key parameter in determining what kind of orbit or trajectory we actually get. And the reason for this is that p is just a multiplicative constant which normalizes the length of the radius. Whereas this epsilon has a more qualitative influence on how r actually depends on theta. So one thing that I mentioned to you is that if epsilon is equal to 0, and then using the definition of epsilon that we wrote, we get that the energy is we should have a circle, because the radius would be a constant. So what happens if epsilon is smaller than 1? Well, according to our definition from 10 minutes ago of epsilon, it should correspond to the case where the energy is smaller than 0. So based on the discussion we had in the previous lecture, what would you expect for the orbit in this case? Roughly speaking, what kind of trajectory would you expect if the energy is below 0? Yes?
Well, we get some kind of bound trajectory.
Yeah. In fact, we get an ellipse in this case. And note that in the circular case, the energy is also negative. So in both of these cases, in general, we get an ellipse if the energy is below 0, but for this particular value, which is a special case, a circle is a special case of an ellipse. So for this value, we get a circle. Otherwise, it's a general ellipse. Okay. What happens if epsilon equals 1? Well, let's have a look. Then we have 1 plus cosine theta, which has a maximum value of 2 and a minimum value of 0. So if this term, when theta equals pi, becomes 0, we have r equals p over 0, which means r diverges. So we should have some sort of diverging trajectory. It's no longer bound. Corresponds to the case of 0 energy. And if you plot this, you get a parabol. And we have one final case remaining. So note that these 4 cases, or in fact these 3 cases, this is just a special case of epsilon being smaller than 1, but these 3 cases sort of exhaust all the possible scenarios that we can have, since epsilon is a real quantity. So if it's larger than 1, the energy is also larger than 1, and we get what is known as a hyperbole. Note that in this case, we can also have a diverging radius for some angle theta. As long as epsilon is smaller than 1, this term can never become 0. But if epsilon is equal to or larger than 1, we can have a diverging radius at some point. So let's have a closer look. Oh, sorry. Yeah.
The energy, should it be greater than 0?
Yeah, my bad. Sorry. Thanks. So let's have a closer look at the elliptical case, where epsilon is smaller than 1, and correspondingly the energy is smaller than 0. Can you live with that being an ellipse? Okay, so when characterizing an ellipse, one usually operates with the two half axes, A and B. If in the special case where A equals B, we have a circle. Now I have drawn the ellipse like this because our expression for the trajectory here has implicitly incorporated the fact that at theta equals to 0, here, we should be at the perihel, which is the point of the trajectory closest to the center, the origo, and this is this point. So this way of drawing the ellipse is consistent with our assumption. So we have a bound motion between R1 and R2. So according to this figure, we can now actually obtain information about these half-axes and how they depend on our parameters. So we have, for instance, that 2a, the major half-axis, is equal to R1 plus R2, the perihel plus this maximum distance, which also has a Latin word, but I can't remember it right now. I think it's ap something. Apogee, right. So R1 is given like this, whereas R2 is given like this. So for a particle moving in a central force with orbital parameter p and eccentricity epsilon, the half-axis is given by this expression. And if we want to dig a little bit deeper and actually reinstate the original quantities, energy, mass, the strength of the potential, K, etc., we can substitute these quantities into P and epsilon. Which tells us that the major half-axis is determined solely by the strength of the potential and the magnitude of the energy. So note that we have a minus sign here, but since the energy is negative for an ellipse, minus E is equal to the magnitude of E. So upon characterizing the sort of orbit of an ellipse, it's also useful to introduce a quantity known as c, which is half the distance between the two focal points. Like this. And we can then show that the eccentricity is given by c over a. And the reason for why I wanted to introduce this c quantity is that for an ellipse, we have the following geometrical relation. The major half-axis, or half of it squared, is equal to b squared plus c squared. And we can convince ourselves that this is true, in particular for a circle, because for a circle, the two foci points coincide. So c is equal to 0, and a is equal to b. So by using this geometrical relation, we get this. And if you're interested in expressing the minor half-axis b in terms of our original parameters, energy, angular momentum, k, etc., we can follow the same strategies over there. We just substitute p and epsilon. So if we do that, we get this. So we see that whereas the major half-axis is determined by k, the strength of the potential and the energy, the minor half-axis is determined by the angular momentum and the energy. So this should mean that if L is very small, it goes to 0, then B should also be small. So we would get some kind of elongated ellipse, like a cigar almost. Which would make sense because then we have a lower angular momentum, since the motion is more rectilinear. So both of the parameters depend on energy, but B depends on the angular momentum. Okay, we'll take a break there.